We are still looking at processes involved in the balance global carbon cycle. Obviously, this always comes down to looking at the atmosphere, ocean, PCO2, carbon concentrations, which is directly related to alkalinity balance in the ocean and the various fluxes we have been looking at, terrestrial weathering, and now we are looking at multiple components of ocean weathering, acid generation in the ocean, and so on. So one of the components that is important and yet is very highly uncertain is the role of groundwater in weathering and alkalinity balance and the fluxes. There are many measurements made. Locally, you can measure directly the fluxes of the alkalinity or CO2, bicarbonates, carbonates, and so on. But when you want to make estimates of fluxes at continental scale and so on, typically isotopes or proxies that give you indicators of weathering are used, like we looked at before, strontium 86, 87, uranium, and so on, based on the time scale you are looking at. So many studies argue that the groundwater discharge, what is generally known as submarine groundwater discharge or SGD, can be much larger than rivers, influx from rivers. This is just a schematic showing how groundwater actually, submarine groundwater discharge happens. One is the fresh water flow, and the other is the recycling of the ocean and the modification and what is salt water submarine groundwater discharge. So fresh SGD and saline SGD. I won't go into the details here. Basically, there is seepage at shore interfaces coming from the unsaturated zone in terms of soil water. Of course, when you say groundwater, you have saturated soil. So fresh groundwater and freshwater flow together puts in some amount of flux that which are products of weathering. So obviously there is a lot of weathering happening by the groundwater as well. As long as you have water and there is CO2 available somehow, or other acids, then you have weathering happening, and that flux is going to flow out. So there is the salt interface, and there are recirculation cells shown here with a confining layer. This is just kind of a typical typology, so don't worry about the details. And you can have saline groundwater discharge above the freshwater discharge, and again saltwater interface, another recirculating cell, and so on. So this is just a schematic, but you get the idea that groundwater discharge are not insignificant by any means, and all the data points to this. So people are using that now to add further details. This paper looks at alkalinity balance of the ocean. Fluxes are in teramoles per year. The traditional alkalinity balance considering river input of dissolved inorganic carbon and calcium carbonate burial. Remember that every time you bury a calcium carbonate out of the circulation, you're going to take away CO2, so that's going to affect alkalinity. And of course, when the calcium carbonate is formed in the water by combining Ca++ and CO2 in various forms, obviously you are releasing one molecule of CO2 there. So compared to silicate weathering, carbonate weathering on land can come back and reform into calcium carbonate and release that CO2 back. Okay, keep that in mind, but look at the fluxes. When you just consider river fluxes, you have dissolved inorganic carbon of 32 teramoles per year with a range in the continental margin. You export calcium carbonate of 36, and there is 23 going buried in the open ocean. Why is there more burial here? Basically because as calcium carbonate forming shells are sinking, the temperature gets colder, CO2 is increasing with depth. All the dead material falling and respiring and other processes increase CO2 with depth. It's lower at the surface because of photosynthesis. So the acidic waters, as you go with depth, begin to dissolve calcium carbonate. And there is a depth at which the rain rate, the amount of calcium carbonate falling, and the dissolution rate are the same. That's called the lysocline, calcium carbonate compensation depth, and so on. If the calcium carbonate shell material gets to get past the lysocline, then it's going to get buried. So the lysocline is obviously much shallower in the coastal regions, so you bury much more calcium carbonate, whereas the long journey to deeper depths in the open ocean is going to dissolve more of it. Of course, production can also be much lower, so you have to look at that. So input is 32 versus output 59 based on the various estimates of carbonate burial and alkalinity balance. But the modification here is to add particulate inorganic carbon of 21 teramoles per year with a large uncertainty coming in through the rivers, and you add additional fluxes from submarine groundwater discharge that we just talked about, which is the main goal of this podcast. Submarine weathering is going to add, so this is 1 teramole per year, 2.8 here. Anaerobic processes 6.2. Remember, methanogenesis and seep waters into the pores and orthogenic clay formation, and that consumption of alkalinity. Organic matter burial, reverse weathering, which we will look at in more detail. We have already mentioned it. And again, you have the same number for calcium carbonate burial in the shelf area and the open ocean. So now you have input of 66 teramoles per year and output of 60. So you have reduced the imbalance of alkalinity by a lot. That's the point. Okay, so here the table, the same results. Alkalinity balance of the ocean fluxes in teramoles per year. Traditional alkalinity balance considering river input of DIC and calcium carbonate burial, and revised oceanic alkalinity balance considering additional sources and sinks. And it's basically repeating the same point but adding a couple of more points. Global alkalinity balance, we looked at riverine DIC, PIC, submarine groundwater, submarine silicate, sulfur burial, denitrification, which is a process that is related to the some species extracting oxygen, for example, from denitrification. If oxygen is not enough, they can split nitrate into nitrite and then release oxygen for their survival. Denitrification happens at various depths. There are large anoxic region where denitrification happens a lot. So organic matter burial obviously takes away carbon dioxide and increases alkalinity balance. So here riverine DIC and carbonate burial balance gives you a global alkalinity balance of 32 teramole per year flux, whereas when you add all these together you have an imbalance of sorry, let me not do it differently. So this is 32 teramoles per year, and when you include these other things, that's 66 teramoles per year of fluxes. Open ocean carbonate burial is 23, and open ocean margin carbonate burial is 36, as we saw. Reverse weathering is not included when we do this calculation, but it's included here with 1 teramole per year. So total sinks here are 59, and the imbalance between 32 and 59 is 27 teramoles per year, whereas when you add these other sources, you have reduced the imbalance to -6 teramoles per year. So you have overshot a little bit here 66 total sources, and total sinks are at 60. Okay, so this gives you an idea that there are large uncertainties, but we have to deal with them because we are talking about geologic evolution of carbon cycle, hence alkalinity balance as well, and how this has resulted in climate regulation along the way. So we will look at a few more processes of ocean marine sediment weathering and ocean crust weathering to see how those fluxes together with reverse weathering also contribute to evolution of the carbon cycle and climate regulation. We have to go through these because we are looking at history of carbon so that we know where it is going in the future and what other enhancement processes may be possible after we understand all these processes, their time scales and their magnitudes of fluxes in alkalinity balance and so on. Okay.